Okay, so thank you for joining me on this rates video. I have to do this a little bit different than I normally do it because we are traveling right now, so I do not have my whiteboard that I normally have at my house, so I'm using my iPad. Hopefully this will still work out. So let's get started. The first thing that we do, of course, is to get the kids' minds awake and thinking about math, and so quick flip arithmetic is still the theme for the week, and Dr. Gilpin still suggested the distributive property, which I totally agree. I feel like my kids are still needing some practice on this. So if I write out the distributive property, you have A times the quantity B plus C. And when you distribute that among that, you will have A times B plus A times C. And I've had some bright math students say, hey, if whatever's in the B plus C, you can just add that together. And that has been true so far for the weeks that we've had. But this time we're going to use a different example with complex numbers and see how this changes. So if I draw some cards, and let's just pretend I draw a 2 and a 3 and a 4. And again, if you don't know this about me, I always plant those first few cards so that I know what I'm working with on the first example, and I make sure I have all my math done and everything else. So my A will be 2. My B, I'm actually going to make it 3I, so I'm using that imaginary number on my B term. And then C is 4. So if I plug that in here, if I plug it into the left side of the equation, that would be the same as, so A is 2, B is 3I, and C is 4. So it'll look like this. You can see right here, we cannot combine those terms inside the parentheses because they are not like terms anymore. So we do have to use the distributive property in order to distribute this out and work it a little further. So that's the same as 2 times 3I plus 2 times 4. And so 2 times 3I will be 6I, and then 2 times 4 will be 8. So 6I plus 8, and that's as far as we can go. We cannot simplify any additional on that. Now, if okay, and I'm going to erase that example real quickly. Okay, so this time I'm going to change it up just a little bit. Here, let me erase these also. And we will switch the cards over and pretend that I have drawn 3, a 4, and a 5. This time I'm going to make 2 of them imaginary numbers. So I'm going to make this A term 3I, my B term 4I, and my C term will just be 5. Okay, so if I plug that in to my equation over here, that's 3I times 4I plus 5. And that 4I plus 5 cannot be simplified within the parentheses, so we have to distribute this out. So I have 3I times 4I plus 3I times 5. Okay, so 3 times 4 will give us 12, but then you also have the I times I, which is I squared. So I'll just write that out so you can see that here. I squared, 15I over here. Now I squared, if you remember, I actually had my daughter write this out in one of the first weeks. So I is the square root of -1. I squared is -1. I with a power of 3 is -I, and I with a 4th exponent just brings you to positive I, or 1, sorry, positive 1, this is a 1, this is a 1, that is a 1, and then, so the only one that has the I cubed is the -I, not a 1, that's a -I. And if you need a little bit help on these or remembering what these are, I just had my daughter write this on a little flashcard, and she keeps it at her desk because throughout all the complex numbers that we've calculated with throughout the semester, anytime we have this, you might have to simplify, and you just need to know what these 4 values are. These are the only 4 she really needs to know. If you want to further understand what these values, like how you got to these values, I have a video that just goes through that, and I'll link it below. Okay, so if you look over here at this chart, you can see that I squared is -1. So that means that this 12 is times -1. And so we just get -12 plus 15i. And that's as far as we can simplify. So I would probably find that in my class, if I get through those 2 examples, that's probably as far as we're getting. But that is fine with me because we definitely need to go through that distributive property more and get more practice with that. They're going to be doing a ton of that in algebra. They definitely need to have a handle on how to calculate with the distributive property. And so this is great practice for them. Okay, we'll move on to the exordium. Okay, so this week the artwork is Targa Florio Vintage Art, photographed by Gerhard Gellinger. So what do you see? I would ask the kids. And I'm sure they are going to have a fun time telling me about the fans and the race cars. And somebody might be able to figure out that we're probably in Italy. And they can say how it doesn't really look like a photograph. It's more like, because the images are kind of blurred, it's almost like on canvas. So yeah, interesting. So we'll see what they say. I would say, where do you think this is if they don't figure out Italy? And then we can talk about how the language is Italian, and or maybe seeing some Italian flags there. And I would say, yep. And when do you think this was? And I don't know if they can tell from maybe what people are wearing in the crowds, but it is a long time ago. So I would say even before I was born, and they'll go, wow, that's such a long time ago. And then I'll say, how do you think race cars relate to rates? And we'll see what they say about that. Okay, and so yeah, the race cars are going at different rates. So one car, maybe this car, had the fastest speed in the race, and at one point in time they were going 200 miles per hour. But maybe the overall speed, they don't keep up that speed, and the overall average speed is like 180 miles per hour. So it's not always the fastest race car at one given moment that wins the race. And actually, this may be the fastest race car at the moment towards the end, and they still don't win the race, right? Because what happens sometimes? Well, you can have crashes, you can have other unexpected things. So it's not always the fastest race car that wins. So this is actually a racing event that started in Sicily. Do you guys remember where Sicily is when we did our drawing in Europe? Yep, it's an island off of Italy. So it started in 1906, and it was part of the World Sports Car Championship between 1955 and 73. So this is meant to be, a long time ago, probably around 100 years ago. And then we'll go through and read the quote from C.S. Lewis, and he mentions a rate of 60 minutes per hour, which is kind of the rate we're moving along in this world. And although we travel at the same rate, we can choose to do different things and accomplish different things during our time. That's kind of what he's talking about. And then we'll read the reflection and see if they have any other thoughts on the reflection as well. And then I would say, any other thoughts on how our cover ties to rates? Okay, now we are back to discussing the invention page, so the I2 page. I would say to the students, tell me everything you know about rates. And they'll probably tell me about speeds and maybe driving in a car and traveling miles per hour. Those would be good examples of rates. So we're looking at some distance over time in that scenario, and that seems to be a very easy one for the kids to understand. The next thing I'd probably do is look at the 3 top graphs on this page. And so the first example that we have, I'll just kind of draw it out on here. it says zero change. Okay, horizontal slope. And don't mind my sloppy handwriting on my iPad. Okay, zero change horizontal slope. The first thing I would want the kids to notice and to pay attention to here is that normally we've kind of looked at this chart and this quadrant, and we've been looking at things in terms of X and Y, correct? But we do not have an X and Y. What do we have here? And hopefully they notice there's a Q and a T. What do you think the Q and the T stand for? And maybe somebody will notice that T is probably time. And if they don't notice or think about it, you can let them know that Q is for quantity. Okay, so we're changing our quantity of something over time. Although in this case, there's no change. There's no change. It's a horizontal slope. It's constant. There's no change. Okay, so the next example that we look at on our invention page is a positive slope. And again, we have Q and T, and what were those? And hopefully they say quantity and time. And in this case, my quantity is going to be shells that I'm collecting along the beach. So I'm going to walk along the beach. Has anybody walked along the beach to collect shells? And we are landlocked in New Mexico, so I might have a few who have never been to the beach, but then I'll probably have some other kids who have. And they'll say, yes, we've done that. And I'll say, do you notice a difference when you are collecting shells depending on the tide? And they might say yes as well. So if you are on the beach and it is high tide, so the water is further up the shore, I'll probably explain that to my kiddos who haven't been to beaches, you would just have a slow increase. So you do have an increase in the shells that you're finding, but it's a slower increase because you mostly have water around you. You're not finding a lot of shells. And then as the tide starts receding, it gets closer to low tide, you're going to have an increasing quantity because you have less water around you and you're having more shells that are left behind. And then as it gets to low tide, the water is really receded from the beach. And so you have a faster increase in the shells that you can collect over the time that you were there because the water's gone. And so now you have all these shells that are left and you can increase and increase how many you're collecting. So that is how the positive slope looks. And that's the example. Now, if we look at negative slope, so this was positive. And if we look at negative slope, I'm still going to use Q for quantity and T for time, but in this case, I'm talking about building a sandcastle. And in order to build a really good sandcastle, you actually need a little bit of water with the sand in order to kind of mud it together and get it to fit together and make stronger sand to make your bigger castle. And so over here, I have water in my bucket, and then my T is still going to stand for time. But, oh no, I have a hole in my bucket. And so because I have this little crack, I have a slow decrease of the water that's in my bucket because it's slowly dripping out of there. And then if, my kid sits on the bucket and makes the crack even larger, I'm going to have a further decreasing quantity because that water is going to leave my bucket even faster. And if the crack gets really bad and it's a full hole, well, now I have a faster decrease. And I'm hardly keeping any water in my bucket. It's decreasing so quickly. So that's an example of how negative slope works. The next thing on this page that you could talk about, and of course I don't get through all 5 of the common topics, but I just kind of list them out in the lesson plan. You can decide which things you want to go through. but there are a number of equations where you have the distance, rate, and time. And depending on which two values you know, you can solve for the third unknown. And so they're just giving you some different examples of what these equations look like and how they relate to each other and how you could set them up so that if you had two, you could solve for the other one. Okay, the next part that they show are a couple different graphs to show some different increases or decreases. And the first example, this one right here, I would say is kind of like a rocket. So you can think of this as you get further along in time. So this is my t. You're actually going faster and faster. And so this is an increasing increase. This next example is kind of like a ball that is thrown. So you have an increase, but it's decreasing and slowing down. This third example, it's kind of like if a parachuter is jumping out of a plane. As they increase in time, they're going faster and faster down until they hopefully open up their little parachute. So they don't keep decreasing at a faster speed going down. So here's my parachute jumper. And this last example is kind of like, this last example right here is kind of like a plane coming in for landing. So they decrease a lot of elevation and then they're kind of slowing down as they're coming along in time and coming to that landing. I want to be in the plane that's landing like this, not the plane that's landing like this. Okay, so there's some different examples and you can kind of give those examples to the kids so that they can see how to understand those. All right, the next area, memoria and arrangement. I'm actually going to point this out in person because I don't want to have to redraw the little gymnast lady. Okay, so on the memoria and arrangement, I just wanted to point out that we have this equation here for the equation of a line is P equals P naught plus TD. So P is our variable vector. You can see the vector line above it. P naught is the constant vector. T is time, and then D is the direction vector. And so they kind of are showing these in the different dimensions. So 1D, 2D, 3D, 4D. I think the thing I'm probably going to point out on here is the image of the gymnast, because here she is on a single axis. So this is just like going along a number line, going along one dimension. Now, if you break it into 2-dimension, the gymnast maybe this could almost be like the floor routine, where they could go in one direction on the X and one direction on the Y. So this is like when they're doing the routine on the floor routine. Now this one has a bar, and so not only do we have our X and Y, but we could be moving upward, up into the third dimension, and that's how the bar can bring us up into that third dimensional space. And then for fourth dimension, so here she is on a bar, so she's moving along X and Y, and she's up off of the ground, so that's her Z. So she already has those 3 dimensions, plus you have a moving truck in a parade. And so you have moving through space in space. And so that's how we get to that 4th dimension. So I'll probably just show the kids how to look at those different dimensional views of the gymnast, and then they just can know that this is a place where they can come to get that line information as they're increasing and learning about that. Then the next thing is to go through, and so the charts, the last note on the charts, this is a lot of the stuff that we talked through on that first page. Here are those slopes. Here's the examples of the increasing and decreasing, where we talked about the rocket and the ball and things like that. So they're seeing calculating with rates, solutions and doing conversions and calculations. And then we have combining solutions and different rates in chemistry. So thinking about how rates go with chemistry, and then growth and decay. And so this is more kind of finance related stuff. And so they probably are not doing a whole lot of that now, although they have a couple of problems on the student section that go through that. So the first page for the student section, I'm only actually going to have the first pair work through this little box right here. And so this was kind of those examples with the rocket and throwing the ball and the parachuter falling down and then the plane landing. And so I'll have one pair go through this section. Then on the second page, I'll have another pair work through this displacement and distance problem. And what I just want you to notice here, so they're showing the vector, which of course vector is magnitude and direction. So it's 20 meters is your magnitude, your amount is 20, and then your direction is, this case, towards first base. And so your distance traveled and your displacement from the origin for first base, in both cases, we're just talking 20 meters, heading from home up here to first. Okay, so if we want to look at the speed, is our distance over time. So 20 meters over the 10 seconds, so that's just 2 meters per second, because we're going to simplify that, 2 over 1 meters per second, or 2 meters per second. Now the displacement from the origin, it's still also 20 meters in that 10-second time frame. In this case, we're calling it velocity. Velocity is displacement over time. It's a little bit different. So this is still 2 meters per second. So in this case, the speed to first base and the velocity to first base are equal for first base. But let's talk about how it changes if you went to second base. So for second base on distance, we still are traveling over here to home, or from home to first, and then we're traveling from first to second, which will be another 20 meters in that, right? So that is our distance that we had to travel. Displacement is talking about how far are we from the origin. So if we are at second base, our displacement, our most direct route, is just this straight shot from second base over here to home. And as a crow flies, this is going to be shorter than the 20 meters and 20 meters. So these were 40 meters to get over here to second base. But from second base, if you did a straight shot over here, it's not going to take that long. And actually, you could use Pythagorean's theorem, right? A squared plus b squared equals c squared. So I could take my 20 meters and my 20 meters squared, add them up, and then get the square root and see exactly what this distance is. But I don't think our 7th graders are learning about Pythagorean's theorem yet, so I wouldn't worry about that. But there is a way to calculate for that. I think in general, the students would be able to see how this distance is faster than if you had to come all the way over to first and all the way down here. So they can just intuitively understand that that distance was longer than the displacement of just going from second back to home. And so they are not always going to be exactly equal, but on the first base example, they are. So I think if we just get through those two problems in class, that's probably pretty good. Otherwise, you can continue to assign something from the additional pages. Maybe just look at here at the way that the vectors are going in one direction or returning and going back in the other direction. So just kind of comparing how your vectors, which have direction and their scalar amount, that magnitude, and how they compare together. So there you go. I hope this was helpful on understanding a little bit more about rates. And please forgive my voice. I'm still kind of getting over an illness and the fact that we are on the road on vacation.